All right, I think Lila, I'm going to recognize you.
Okay, well, I'm going to recognize Antha and say it's exciting to be here, and I'm really interested in hearing how any of this science has affected or informed anyone's faith. And one of my questions about this is, if we accept that the universe, the Big Bang, was the result of a quantum fluctuation, it's just not very satisfying to me. It kind of leaves you with, well, there's multiverses, but we can't prove that. And does that mean God is a quantum fluctuation, or was God the thing that just kind of tickled the singularity and poof? Any ideas?
Well, it's been hard for me to believe that, Alice, there's so much order, so much life, so much, just order. Just came out of chaos. So I have to believe in God. There's reasons I believe in God as a personal God as well, and God as an actor in our world. But anyway, it's hard for me to buy that too.
So pushing against entropy, if you will.
Right.
Mm-hmm.
Lila, do you want to repeat that now that Paul has made it on and Herb has made it on as well?
Hi there. So I was just making the remark that if the universe, the Big Bang, occurred as a result of a quantum fluctuation, where does that leave a concept of God in the creation? And is God the great perturber that poked the singularity and poof, the universe and the multiverses came into being? And it's not personally very satisfying, but quantum fluctuations are a thing, and I think we're on firm ground with that theory. So I'm just kind of hanging out with that.
Well, the point that I made previously was that if you calculate what the cosmic constant should be on the basis of that idea, you're off by a factor of 10 to the 120. So clearly some work needs to be done to sort of shore up that hypothesis. I mean, you could equally well say it's the Easter Bunny, but with a miss of 10 to the 120 power, that may be equally plausible. So the other point is that science should not deal with the question of why. It's supposed to deal with how, what happens and how it happens. And then interpretation of that is up to philosophy and religion to put it in personal context. So as soon as we start asking questions about we're unhappy with the possibility that it happened that way, then that's not something science deals with. We're trying to get the answers as best we can on the basis of available information. And the interpretation of it is not something that science should be doing. As a person, a scientist can make a decision about how they want to put it in context. But as a scientist, as Joe Fry used to say on Dragnet, just the facts, man.
Lila, how did that feel?
Yeah, right. Yeah, of course, I love science, being a woman of science. But, I do seek to, I think, attach meaning, as Paul is saying. So that all feels right. It just doesn't feel quite complete for my heart. I don't know. I don't know where I'll go with that.
Well, I'll make some comments later that may have some relevance to your comment just now. I'd like to spend some time today talking about reconciliation of the Fermi paradox and the Drake equation and where that leads us on the basis of what we know now. Enrico Fermi said in 1950, where are they? The context of that was that he understood that he had participated in a new energy source that seemed to be unlimited, as nuclear power. He also knew that we were likely to be going into space with humans in the near future. And so he made a sort of a leap of imagination that says, we know from what we see in the universe that there are many, many stars that are much, much older than the Earth, billions of years older than the Earth. So it's conceivable that advanced civilizations could be millions of years ahead of us in their development. And he made the following argument, that you find spiders and roaches on every island in the world within a short time of the island's formation. It's not because roaches and spiders evolved there, it's because they can be transported there on a time scale that's very short compared to evolutionary time scales. So his argument was that whoever was the first civilization in our galaxy would likely be able to eventually proceed at the rate of, I think he postulated, 1,000th of a light year per year in sending out self-replicating robots, and then later civilizations. So in that scale, it takes somewhere between 10 and 100 million years to totally populate the galaxy. It takes a lot longer than that for intelligent life to evolve on a planet. So the idea was it's easier for the first civilization to reach every part of the galaxy on a time scale that's short compared to the time that life would arise at different locations. So the idea is we ought to be hip deep in the descendants of the first civilization. And if we're not, then maybe we're the only one. And this is where Frank Drake came in a few years later. He postulated the Drake equation, which says how many concurrent communicating intelligent civilizations there should be in the galaxy based on what we know about the way life forms, the way planets form, and so on. Now, a number of the terms in the Drake equation have been pretty much honed down to a fine point in terms of we now know that most stars in our galaxy have planets. We also know that a lot of these planets are in a habitable zone. Plus, our idea of the habitable zone has grown because we now know it's possible to have life on places like Europa or Callisto or Enceladus and so on, that don't depend on the light from the sun as an energy source. It can be gravitational tidal heating. It can be black smokers at the bottom of an ocean. It doesn't even have to be a planet that is open to the world with an atmosphere in between. So, for example, there's virtually no atmosphere at the surface of the Jovian moons. But if there's a planet-wide or moon-wide ice cap that's several kilometers thick, you can have a saline ocean under that has black smokers that might have life. So the definition of where life might be has grown. Also, our understanding of life forms on Earth, because we now know that we have critters, the archaea, that can survive in rather extreme circumstances. So the number of possibilities for the Drake equation has grown considerably. So I wanted to talk a little bit about that. What is the definition of life? Are viruses alive, for example? The basic physics definition of life is fairly straightforward. It's transfer of electrons. It's basically charging and discharging chemical batteries. So life forms on Earth basically assemble molecules that have electrons in a higher energy state than they had before when they're storing energy. They're charging their batteries. They basically break down molecules into states that have lower electron energy to get that energy for their purposes, for growth, for locomotion, for reproduction, and so on. So in that sense, the chemical basis for life is charging and discharging the chemical batteries. And we now know that there are a lot of different ways to do that on Earth. For example, the simplest life forms we know of You can call it water on the rocks. It turns out that microorganisms, primarily archaea, but not exclusively archaea, several kilometers down in the earth, can use the thin water film around rock particles, and the rock particles have iron as part of their composition, and they basically change the oxidation state of the iron. So these are the same critters, by the way, that are causing the Titanic to decay. They're iron-eating bacteria. Incidentally, the red color of the surface of Mars comes from oxidized iron. It's rust. So that might be a clue that there have been life forms at Mars before. The other thing that we find is that life takes many different routes to get its energy. We have the iron-eating bacteria. Early forms of life used all sorts of different strategies to do the electron transfer. Fermentation, for example. Photosynthesis came much later, but we know that there are various processes that went on. Conversion of energy in hydrogen sulfide, for example, with the black smokers is one way life does it now. Methane production and methane consumption. And it's not that life forms went from one style of electron transfer to others later. All those different processes occur concurrently on life on Earth today. In fact, one of the great extinctions about 250 million years ago was when the sulfur-producing bacteria, or sulfur-eating bacteria, took over the entire Earth and created an oxic condition, probably because of volcanism releasing a lot of sulfur into the atmosphere. So life switches back and forth between its necessary feeding strategy depending on circumstances. So in that sense, life is very flexible. And that's another thing that you need to consider in looking at the Drake equation. Now, what I did, I think Mike sent out the sheet that says life zones and galaxies. What I did was try to look at what the factors in the Drake equation are, and I artificially adjusted all the terms except the last three to come out with a product of about 1. And we can argue about whether it ought to be a 10th or 10, but order of magnitude, that's probably a pretty good guess from what we know about Kepler and how many planets there are and where the planets are. So if I start with that, then we go on to the definition of intelligence and the definition of communication. How many intelligent species are there on the planet Earth? And that depends on how you define intelligence. We like to think we're the only one, but if you use something like use of fire or tool use, it includes a lot of different species over a lot of different years, going back all the way to Lucy's time. We know, for example, that there are smart mollusks, octopus and squid actually exhibit puzzle solving ability. We know, for example, that among the dinosaurs, the only dinosaurs still with us are birds, but some parrots and crows are very, very smart. Caledonian crows will take a wire that you give them and bend it in the shape to extract a nut from a beaker. We also know that whales that were land animals that went back to the sea have very complex social societies, and they have different dialects. They're able to communicate with each other very well. Among lower carnivores, meerkats, who are mongooses, they have a complex society, and they actually have a vocabulary for warning signs of birds, snakes, and other critters. Among primates, we apparently are alone now, but we had a number of close society relatives, including Neanderthals, Denisovians, and even some unknown things that show up in our DNA. So how many of those were intelligent? We can say that there's a handful of different creatures on our planet that exhibit some level of intelligence. So how do you figure out what that factor is? Now, one way to figure out what that factor is to figure out how many species we've had on planet Earth. Since the beginning, of higher animals, we know that we're about 0.1% today alive. That is, we're on Earth, 1 out of every 1,000 creatures that ever existed, complex creatures, is still alive. So that means the number ought to be 10 to the minus 3 for our present existence. If we ask, what's the definition of communication? Well, the definition I like to use is, when was the first time we were able to transmit and receive with enough power and sensitivity to speak to anybody else in the galaxy? And that's only about 60 years ago. That's when Arecibo came online. So the question is, what are those last 3 numbers in the Drake equation? And to reconcile that with where are they, there must be a bottleneck somewhere that indicates that n is either very small or there's something wrong with our assumption that science keeps marching forward indefinitely. The other question is, how do we know ET's phone number? And I've given Mike a graph that shows the background in radio wavelengths of the galaxy. Did you guys get that, by the way? It's a graph that shows
Well, I might need to share my screen to put it up. Some people are having trouble finding it. I know it's coming in this Wednesday.
okay.
Let me see. This is the one. Is this Life in Zone? This is Galactic Waterhole, right?
Yeah, exactly.
Okay. Let me share my screen
Okay.
and I can show that to us.
Okay.
Here we go.
Yeah. Okay, this shows the radio noise in our galaxy. You can see the galactic background is the line that comes down from the upper left to the number 1 at the bottom in frequency. On the right are the absorption lines of our atmosphere. And if you see that there's a minimum between the galactic background and atmospheric emission, it's in the region of the 21 centimeter and 18 centimeter lines of hyperfine hydrogen and hydroxyl. So the point is that this is a natural sort of clear frequency, clear channel to communicate across the galaxy, but even better than that, it's also the frequencies that any intelligent civilization would be looking at, because that's used to map out the arms of the galaxy. The H comes from hydrogen regions where it shows where the spiral arms are. The OH shows where stars have processed to the point of hydrogen, of oxygen, nitrogen, and carbon. So using those 2 lines to map out the galaxy is a natural process for understanding where we are in the galaxy. And these frequencies don't get bothered by dust or any obscuring other material in the galaxy. The combination of H and OH, of course, is water. So radio astronomers refer to this as the water hole. It's where critters on Earth meet and interact. So the logical place to look is between H and OH and send and receive messages there. So that's the water hole. Okay, so I also sent out another thing talking about life zones and galaxies. The idea behind this is that in the galaxy, because of the way generations of stars form and process elements into heavier elements, that there's a Goldilocks zone. If you're too close to the center of the galaxy, things are too violent. Lots of generations of stars form there because big stars form close in. It's the one that says life zones and galaxies.
Oh, okay, this is not the right one.
No, it's not the right one.
Okay, I can fix that.
Okay.
Okay, does that look right?
No, that's still the same one. It says it's the light
Oh,
blue heading, life zones and galaxies.
Yeah. Okay. Okay.
It's text, yeah.
Okay. This one?
Yeah.
Okay.
Okay. The basis of this is the reason the central bulge is present in galaxies like the Milky Way is because stars cannot settle down to the disk because they're being constantly disrupted. And so the bulge is due to the gravitational disruption of the disk, sending stars out of the plane of the disk. The other idea is that because the density of stars is so great, it'd be a great place to look for highly evolved planetary systems. But the same chaos gravitationally that causes the bulge to exist disrupts planetary orbits and, in fact, flings stars around. Also, where you have a high density of large stars, you have a high density of supernova. So it's a fairly dangerous place to be on the basis of both gravitational ballistics as well as radiation. As you go further out from the central bulge, the environment gets a little bit less hazardous for those reasons, but also what happens is fewer generations of stars have lived and died. And so if you look at galaxies like the Milky Way or Andromeda, you see a gradient in metallicity. You see that the outer regions of those galaxies are deficient in heavy elements. And because we're made of heavy elements and our planet is made of heavy elements, that's clearly at some point not going to lead to high density of planetary environments that life can exist in. And so the idea is that there's this Goldilocks zone at a distance away from the center of each galaxy. And it's a disk that extends over some region, but we happen to be about 27,000 light years away from the center of the galaxy, and we're here. So that's probably a good place to say it's the Goldilocks zone. If you do that, then you can calculate, that was the figure you had up before, Mike, that table that was put up. That table basically shows the result of assuming that we're in the Goldilocks zone. And what I did was set all terms except the last three equal to 1. Then this is the product of n, the number of communicating civilizations. Obviously, n has to be at least 2 for it to work, because 1 doesn't have anybody to talk to. So I started off with 2, and I distributed the number equally statistically around the ring that's 27,000 kilometers from the center. So it shows what the product of the fraction of intelligent civilizations and the fraction of those that can communicate is going to be on the far right-hand side. It also shows in that T2 min, the amount of time it takes minimum for a two-way conversation to occur in years. So we've been communicating for roughly 60 years. In order for us to be able to talk to anybody and get a response, we'd have to have 1,000 civilizations in a galaxy or more. If you look at the number, let's take the extinction of life on Earth and say that we're down to the level of 0.1%. So that's 10 to the minus 3. Let's say that the probability of intelligence resulting in communication is a factor 1 in 10. Then the factor on the right that's closest to figuring out the right number is that 3 times 10 to the minus 4, which gives you 33,000 years round trip communication time. So in other words, on the average, we'd have to be transmitting for a time much longer than the age of any civilization on Earth in order to get an answer. So for this reason, I think that no matter how you manipulate Fi and Fc, there are a lot of reasons why intelligence doesn't lead to communication. So if you take the number of different intelligent groups we have on the planet and say it's a handful, what do you need in order to get interstellar communication capability? What technology do you have to have? Well, one technology you have to have is metallurgy. In order to have metallurgy, you got to have fire. You can't do it if you're the intelligent critter in an ocean planet that has no dry land. You can't do it if the intelligence rises under an ice cap 3 kilometers thick. So the step from intelligence to communication is probably a lot harder than what Fermi imagined. And so my number, I figured that N is somewhere in the range of 5 to 25, but probably not more than that, which basically says we're going to have to listen for a long time after we send to get a response. The oldest continuous civilizations on Earth are something of the order of 6,000 or 7,000 years old. So as far as where they are, the fact we haven't heard from them is not the least bit disturbing. You're going to have to wait a long time if that number is that small. So that's my take on the Fermi paradox and the Drake equation. But there's also some other considerations. Fermi, when he said, where are they, assumed that science would progress at an ever increasing rate over spans of millions of years. We're now running head on into several things we really don't understand, like entanglement, like dark matter, dark energy. The question that Lila raised about quantum fluctuations in a universe we have no metaverse that we have no access to. So it's entirely feasible, in my mind, or possible, that the problem is science runs up to an obstacle where no matter what we do, we don't have the means of reaching beyond that. We can't go to an energy level high enough to find out if there's anything more fundamental than quarks and gluons, because it would take an accelerator larger than the Earth to reach that kind of energy. We also have limitations in a lot of other areas that tell us we can't see part of our own universe, for example. We can't see beyond about 3% or 4% of the volume in the present universe because it's forever outside our light cone. If dark energy is actually producing acceleration, as was pointed out in Tyson's book, we're going to see over many millions of years less and less of the universe, smaller and smaller fraction, till eventually, many billions of years in the future, we're not going to see much of anything. So the question, besides the fact that we probably will not be here, we certainly will not be on Earth beyond a point about 500 million years from now, because the Earth will be incinerated. So it may be the reason that we're not seeing other civilizations here is simply because that's just the way it works. You don't gain knowledge exponentially. You eventually use your knowledge to run into those barriers on any further knowledge. In other words, you get to the point where here be dragons.
Paul,
Okay.
another way of saying what you're saying is that N could be very large, but if travel and communication are limited by the speed of light, we could be just so spread out that we never interact.
Well, the point is, in our galaxy, which is the only possibility of communication, the numbers, the probability of intelligence and communication would have to be combined one to produce N larger than 582, if you look at that chart. So it says that even if there's such a high probability and we're limited by the life zone in the galaxy by factors that are determined by the way stars evolve, that the number can't be really large. So the idea that Sagan had in conjunction with Drake, that there are tens of thousands of civilizations communicating in our galaxy is probably not correct for the reasons I just gave. But there's also another thing. We think we have the phone number for ET, the water hole. But here's the issue. Sagan felt that if we finally did hear from somebody, we'd be breaking into interstellar network where a bunch of different societies are talking to each other. Well, here's what's wrong with that. It's extremely energy inefficient and extremely slow in terms of maximum bit rate to transmit even with a receiver and transmitter as powerful as Arecibo. The most likely means of communication, once first communication is established, once we establish somebody else is there or they establish we're here, would be to use lasers at optical wavelengths, because the bandwidth on the laser at optical wavelengths can be tens of thousands of times greater than the bandwidth of radio telescopes, which means that once we know they're there or they know we're here, we would try to communicate by establishing a link with lasers. But the problem is that is unidirectional. That means you'd have to happen to be in the right place at the right time in order to see the flash of the laser coming and then realize you're, intercepting communication. And so once you get past the radio telescope phase, if you want to exchange a lot of information, you're going to do it by lasers. And there are now searches for happening across the beam of lasers between communication between civilizations. So the radio telescope is a means of establishing something's there, but it's not the means of communication to be used.
Paul, Arecibo failed pretty distressingly and spectacularly. Is there something else that's taking its place?
Well, the Chinese have a radio telescope about 5 times bigger. And there are also some in the works, including an Arecibo-like array much bigger on the backside of the moon. I'm not sure how that fits in our present budget, though. But let me add one last thing. And this is probably a good forum to try to make this distinction. This forum has been looking at the physical side and the spiritual side of what we understand about the universe. As I started to say earlier, the job of a scientist ought to be simply saying what is happening and how did that happen? That is to get to the physics behind it, to understand the mechanisms. But our job is not and should not be to say how you interpret what we come up with. It's equally wrong for a physicist to say you should believe this over a religious belief, as it is for a religious person to say it couldn't have happened that way. I mean, the last time historically that happened was when Galileo committed the heresy of saying that the Earth was not the center of the universe. Now, the church, to give it credit, only took 4 centuries to give him his get out of jail free card. But hopefully today, that sort of thing doesn't happen. Anyway, that was my statement.
I have to say I agree with you, though things like quantum theory tend to raise even in scientists and physicists, definitions of what does it mean. But on the other hand, there's various arguments one way or another in that realm, and you really can't prove.
Well, the thing about quantum theory, it doesn't make a whole lot of sense, but as Eisen says, the universe has no obligation to make sense to us. But the point is, quantum mechanics has contributed trillions of dollars to the world economy because it does work. It's the basis for a lot of semiconductors. We're now trying to build quantum computers that can solve problems that are unsolvable by ordinary means.
Right. Yeah, I mean, when I was coming out of school, lasers were something that people were playing with, and
Right.
some people were saying, "I don't think we'll ever come up with any use for that," and voila.
Well, I was talking about lasers in space for our communication. It turns out that lasers and fiber optic cables carry roughly 10,000 times the bandwidth of communication satellites.
Well, the other advantage of a laser is its light is coherent. They tend to stay together and not spread out as rapidly as other light sources.
Well, but in fiber optic cables, they actually do something better than that. They produce a gradient in the index of refraction that keeps bending the laser light back toward the center.
Yeah, but it's going to be tough to lay a cable or a fiber optic cable from here to the moon, for instance. But
Yeah. Okay, so I'm happy to answer any questions left over from any of this. There may be a few.
So Paul, I had one on life. I was listening to a podcast and they were talking about a theory out of the University of Glasgow about assembly theory and about that you could test for life based on the complexity of molecules that you found. Do you know anything about that?
What is it called?
Assembly theory.
No, I haven't heard of it.
All right.
Anthony, do you want to tell us more about it?
Well, the fundamental idea was that the more complex molecules are in volume, not just like one random one from a lightning strike, but a lot of gasoline or something is too complex to have just occurred at random, and so it's an indicator there's life. So if you can test for how complex the molecules are in a sample of something, then you could have a kind of a limit and say if they're more complex than this amount, then that's an indicator that life was involved. Well, and he's trying to get these things onto probes going up soon.
Well, one of the questions that arises in the definition of life is exactly how laid back can it be and still be life? So for example, some of these microorganisms, especially archaea, that live deep underground, that live on water on the rocks. It turns out for a long time, people didn't recognize that those critters were alive because they would bring up a core sample from a drilling thing and measure it, and there's no noticeable sign of metabolism. But they knew something was causing a change in oxidation state of the iron, and they couldn't figure out from a purely inorganic sense how that happened. So what they did, they tagged the substrate with radioactive tracers, and they waited several months, and they came back and they found out, yep, the critter's alive. It's just not very energetic. It couldn't make good cocktail party conversation. And so the distinction of alive or not is fairly complex. There are a lot of critters that can form spores that can last for tens of thousands of years. And you get the right conditions, the spores revive, and now you have another organism that's active and shows normal signs of life, metabolism, and so on. But they can exist as spores under duress, under drastic conditions for very, very long periods of time. And that may well be what happens to life in other places in our solar system. It may be that conditions aren't right for them to be actively alive all the time. But when conditions are good, they quit hibernating, they come out, they reproduce. A lot of seeds of plants on Earth do exactly that. They will be buried for long periods of time until the right conditions come along, and then they sprout, they go about their normal activities and then form a new generation of seeds that is again dormant for long periods of time.
All right, so I'm probably the least sophisticated person on the screen. I just have to say this. I'm still, I mean, this definition of life, I think what I remember from high school biology, which is like the last science class I had, was that the virus is in a weird category because they reproduce, right? They're able to replicate themselves, but not on their own, right? So this definition of life is still intriguing to me, like how complicated that is, particularly when you think about phrases like life begins at conception, or things can self-replicate, or they can't self-replicate. Would you speak a little bit more about the definition of life?
Well, from a physics standpoint, it's fairly straightforward. Life does what atoms do. Okay, that's the simplest definition. Every process that we look at in life is something we can identify the physics behind it, like transfer of electrons to charge chemical batteries or discharge chemical batteries. Same thing with the questions that you just raised about viruses. An interesting problem is that we really don't understand how viruses started. There are basically three theories. One theory is that viruses were once fully replicating cells, but they lost the DNA need for replication when they found out as parasites they could take over the DNA of the host. The other idea is that they were the first life forms, but then the problem is, how did they reproduce? Then you have something in between that says they were they developed with a symbiotic relationship that turned into a parasitic relationship. And that the viral particles that we see, which are basically nucleic acid with a protein coat, are the spores of the earlier life forms that had a symbiotic relationship. So with higher animals, they're parasites that only reproduce in certain hosts. And some parasites have as many as 4 different consecutive hosts before they reach maturity and can reproduce themselves. So things are complicated.
So my car battery might actually be alive, except it doesn't communicate very well, because every once in a while it tends to croak on me for sure.
Well, if it can reproduce itself without you having to go to O'Reilly's, then it probably qualifies for the definition.
Thanks.
Well, one answer to the question is here on Earth, and that could be a very limited view of what life is, but all life on Earth exchanges carbon with the environment, whether it's through food ingestion or photosynthesis or whatever. And so you can determine if it's alive by looking at, well, once it dies, then the carbon-14 decays because it's not exchanging carbon anymore with the environment. And you can see that it's not alive anymore. For instance, dinosaurs had a certain amount of carbon-14 in them, right? But once they died and turned to fossil fuels, there is no carbon-14 in fossil fuels. It's all decayed. It's gone away because it's not exchanging anymore.
Carbon-14 in fossil fuels has to do with how long the fossil fuel has been buried underground.
That's right.
The problem is that Nick asked us a question about the effect of magnetic reversals. And for a brief period of time, the magnetic field of the Earth doesn't protect the surface of the Earth from radiation. Well, it turns out the only effect that you have to worry about is it resets the carbon-14 clock, because the extra production of radiocarbon by the radiation coming in has to be allowed for. And the way they determine how to set the clock right is tree rings. They count tree rings and measure the carbon-14 in the rings, and then say, okay, we know that from the growth cycle, this tree is this old, but we also know from the radiocarbon dating that the date is not correct. So they basically say shift.
Mm-hmm.
But on a much more basic scale than carbon, actually critters don't exchange carbon, they exchange electrons. And a lot of the electrons are switched or transferred between carbon carbon-based molecules. But really, that's what life is doing. It's not switching carbon. It's using a carbon-bearing molecule to either produce another molecule that has a higher energy state for that electron or a lower energy state, depending on whether it's charging the batteries or discharging the batteries.
Yes.
This is interesting because I didn't think most people think about life this way, like interacting with energy. That just seems like the non-standard definition.
Well, from a thermodynamic standpoint, it's the only one that makes any sense because life as a closed entity cannot survive. So life has to use the environment to create a wider environment, to a wider system to be able to exist.
So does that
Feels like
mean that community is woven into like the fabric of being? That seems like you're resisting what I would call individualism, because nothing can be a rock unto itself and be alive. Is that what you're saying?
No, I'm not. I'm simply saying that from the standpoint of thermodynamics, life cannot be a closed system. It has to be part of a larger system to be able to exchange energy, pump electrons up in energy or let electrons down to use energy. So from the outside, there has to be a source of something. For example, the life forms that live at black smokers are using the energy produced by hydrogen sulfide or methane or whatever, and the temperature difference between that vent and seawater to derive the processes that they need.
Which is, I think this discussion, I didn't hear it so much early, started with the discussion of entropy, but if there's only entropy, the process occurring, then we're going to eventually die out. But we do recharge our batteries and rebuild.
Yeah, but we recharge our batteries by using energy that's available in the environment.
Yes.
Yeah. So for example, photosynthesis, which occurred a couple of billion years ago for the first time.
I remember that.
That's simply an organism having a molecule that can absorb the light, and it can use that energy for production. So the purpose of physics is basically to get things down to the basics. What you try to do is reduce everything you see to the most basic mechanisms. And it doesn't deal with why, it just deals with this happens and here's how it happens.
So Nick put in the comments that some have proposed that life is an exchange of entropy. We consume lower entropy food and produce higher entropy, e.g. carbon dioxide.
Well, yeah, I mean, life is a flow of entropy, just like any machine is. Although I've seen in the last generation, there are apparently some teenagers who defy rules of entropy.
And how is that?
Some gymnasts seem to defy gravity. So.
Yeah. Well, there was an interesting article published in some psychology journal some years ago where this guy proposed, apparently seriously, that gravity was simply the perception of something. And that if you change your perception, you might be able to defy gravity. So, I would have just said, here's a tall building, step off and let's see how your perception changes on the way down. Well, guys, I've enjoyed this. It's been great fun for me.
Thanks, Paul.
It has been.
Enjoyed it too.
It's extremely meaningful, Paul, because again, there's lots of folks like me who haven't had a science course in a long time. So it means a great deal to expand not only my knowledge, but my sense of wonder and awe. And I think actually Tyson's book did a really good job of trying to do that. I think that was the vantage point he was writing from, albeit not a religious one, not explicitly. So I'm really grateful. This is, like I've said with lots of pride, we're sort of probably one of the few places in the country that could pull this off. And I love that.
Paul, I should mention that I did pull out the Drake equation and made a few assumptions, and I calculated 15 million. So I'm gonna have to go back and look and see where it's only 5 or 50.
Well,
There's a book that is an astronomy book, which Paul's talks have caused me to go back and look at again. This one was in 1985, and it came up with an estimate using the Drake equation between 100 and a billion. Now, 1985, so there's probably some other assumptions that have been more clarified, as Paul mentioned, but could be a small number for sure.
well, the main thing that's changed in the Drake equation from the time that Drake first wrote the equation and he and Sagan got together to come up with N is that the first part of the Drake equation, the numbers have gotten larger. But the last part of the Drake equation, the numbers have gotten smaller. So, I mean, what's the lifetime of an intelligent civilization?
True.
And does intelligence also equate to survivability? If you're able to build bombs that can blow the whole society apart, I'm not sure that that's a logical conclusion.
Or consume all the available resources.
Yeah, consume all the resources.
Yeah.
George Carlin, who's one of my favorite comedians, had one skit that says, people say we're destroying the earth. He says, nope. He says, the earth's going to be here. We may not be.
Yeah. Well,
Antha and
Antha,
Lila, I know you've prepared, you all don't know this. I'm an insider on this. This is part of the thank you, is that Lila and Antha circulate these documents ahead of Sundays that are like riddled with talking points and data and like fantastic questions. So, I mean, the amount of human labor and thought and wisdom that goes into these Sunday mornings is like, again, way past what you might think. So tremendous gratitude to all three of you for not only showing up, guiding us through this book, but also producing resources. But you've got a lot of questions for this week, and I want to make sure we segue so that you can do some of those in the next 10 minutes.
Antha, go.
All right. Well, I will start with my favorite one, which is the last chapter of this book, if y'all have gotten there, is full of kind of Tyson philosophizing about the cosmic perspective and what that means. And that his claim is that it's spiritual and redemptive, but not religious. And I was wondering what people thought about him claiming that the cosmic perspective was redemptive, but not religious.
Guess I've always wondered what spiritual but not religious means. Yeah, never figured that out.
I'll say that again. Spiritual may mean you don't assign your belief to a particular religion.
Yeah, religion itself is a really tough word. I used to teach this world religions class to 8th graders out in La Jolla, and they study the big five, right? Judaism, Christianity, Islam, Hinduism, Buddhism. And then at the end, we would tack on things like, Baha'i and Taoism and things like that. They would present those. But we always started with this really sticky bit, and I'm probably the complicator. I mean, we spend 2 or 3 days talking about what does religion even mean. And there's as many definitions as there are people in the world. But that's one of those tough ones, right? The one I usually settled on comes from one of my teachers at Emory, Luke Timothy Johnson, who called religion a way of life oriented around ultimate power. Pretty short and concise. You read a lot of other ones and they include things like rites of passage and rites of renewal and holidays and stuff like that. But this way of life around ultimate power is kind of interesting because in my own head, that seems to represent spirituality as well. I could be wrong, but the two certainly can at least share some area in a Venn diagram. Rhonda.
My take is, religion is like what you said, and it seems that you need to adhere to a set of principles. And, churches do that to varying degrees, where spirituality to me is having a relationship with God and the Holy Spirit and what connects us all, and kind of focusing on trying to connect with everybody in with a positive will. It's so easy to fight among ourselves, but to try to make positive goodwill connections with people and maybe have some, something productive out of that. And I was influenced when I was 12. I read 2001 Space Odyssey, and it gives you this idea that a civilization advanced so far that they're not physical anymore. So it's like, I look at Genesis as people in ancient times trying to figure out why things happened and what made things happen. And, now we've been enlightened by science, and I'm not sure we'll ever understand the beginning of physical things. But I picture God, existing now, his name, I am. And it's hard for us to understand, but maybe he is just permeating, not even he, God is permeating everything in this connection. The spiritual connection is what we should be looking for.
Well, and I agree that I certainly find connection in the cosmic perspective and in science, and that we're all part of this vast, amazing universe and made out of the results of supernova. That's certainly connects to Rhonda's everything being connected as part of being spiritual. What do folks feel about that being redemptive?
So, I can see the redemptive part in if a person can change his or her point of view and be less self-centered by just experiencing the awe of the vastness of the universe and of creation. I think that can have a redemptive effect on a person, awe and wonder. But that's kind of as far as I could see it as redemptive in terms of a person changing beliefs or behaviors.
Incidentally, Tyson objected to being labeled as an atheist. Atheists tried to claim him based on some statements he made, and he firmly declared he's agnostic.
Yeah, I kind of gathered that from his book.
He's an interesting guy, though, in that he leverages like statements from world religions. It's interesting how he uses, spiritual language, particularly religiously embedded language, to talk about things like awe and wonder and connection.
Well, there's one other part that sort of comes into what Tyson talks about, and that is from a mathematical or physical standpoint, why do we expect that a part can understand the whole? I mean, it's presumptive and also somewhat egotistical. And as Tyson says, the universe has no obligation to make sense to us. Or the religious corollary, that is, God doesn't owe us an explanation.
Yeah, that's actually how the book of Job ends up as well, which is pretty interesting.
Yeah.
Sometimes it seems to me that spirituality and perhaps agnosticism differs from religion because it doesn't require the orientation around an ultimate power, and therefore you're not responsible for your actions or behavior.
Well, there are people who are extremely moral in the sense of humanism who don't necessarily connect with a religion. They believe, and there's basis from anthropology that getting along with your fellow creatures is advantageous to your genes.
Freud said, I am moral, but I don't know why.
Yeah. Well, anthropologists say the reason you have morals is because that increases the chances of your genes proliferating.
This is actually a pretty good ending, because one of the things that that's been put forward, we actually talked about this early on, was whether or not we'd be reading this anthropological book called Sapiens. And so that's something to hold on, because that book touches on this question really deeply and frankly pointedly. So maybe that's in our future. I wish we had more time to leverage this, but I have to go to church, sadly. So I'll be happy when I get there. But for the next 15 minutes, I'm allowed to be sad to cut this short. Paul, Lila, and Antha, thank you so much for sharing not only your knowledge, but your organization and your leadership, your gifts of teaching, the numerous resources you've made for us, and as always, your patience with unsophisticated folk like myself. Really, really grateful. And yeah, I'll see everybody soon.
It's been fun.
Thank you.
Thank you.
Thank you all very much.